Okay, so remember this, F equals Bill. We're going to use this today and not use sine theta because we'll do everything at 90 degrees. So let's say we had a magnet here that was north and another one that was south. Now the important thing that we're going to look at here is we're going to say that we have a current carrying conductor through here, and this current carrying conductor is fixed. It can't move. Okay, so there's some wires we're going to attach to a power supply, and what we're going to do is we're going to put a current through here. Now these magnets are actually just sitting here. Okay, and if they were sitting on a scale, so there's a big scale underneath, they would be pushing down with some sort of weight. Okay, so there'll be some sort of weight pushing down on that scale due to the mass of both the magnets. Now if we've got this current applied, then it's going to create a force. Okay, so if you use left-hand Fleming, so remember FBI, then the force is supposedly up on the wire. Now if the wire can't move, then you can still have that force applied to it, but there's some other forces everywhere else to keep it stationary. But also because of Newton's third law, there's actually a downwards force applied to the things creating the magnetic field, because you can't just create a magnetic force without the equal opposite one. So both those magnets are actually going to feel an equal opposite force in total. Okay, so it'll be half F on each. So this will actually give you an apparent weight. Okay, you'd actually get extra weight. It would push down harder on the scales. Let's try a different way. Let's look at a seesaw. Now on the seesaw we are creating a current along a wire, and this wire is balanced in the middle like this. So it can rotate this way or that way. That's just a wire with a cell attached. Okay, and even if we actually include let's include an ammeter as well. Let's say they're the massless, but it doesn't really matter. We've got this thing balanced. Okay. Now, if we knew things like the distance to the side, we knew the whole mass of the thing, then we can actually work out some moments. Okay, and we could say that if we put a current through this wire and we had a magnetic field that was fixed this time, so these magnets are attached to the ground, so north and south on each side of that wire, and we're going to try and apply a magnetic field across that bottom wire, then that wire is going to feel a force either up or down. Okay, now that will create some sort of moment, and if you can work out that moment, then you can find out the B, because if you know the current from the ammeter, you know the length of that wire, the red part, you can find the B. Well, so how do you find the moment? Well, if we apply a force, and this thing will want to rotate, let's say to the clockwise direction, because we're applying a force, so that must be the force going downwards. So we're applying that force going downwards. What we can do, we can add known masses on this side to balance it up. and depending on the weight of those masses, we can then solve for B, I, L. That's assuming that the distances here are the same. If they're not the same, well then you just have to use your moments equations that you've done before.